So hopefully you can see that. I think you can. Let me make sure my sound is off. Yep. So if you have questions, make sure you put them in the chat. I have a couple of questions that people emailed me. You can also email me questions. So I don't have material. I'm not planning on teaching anything new. But if you have questions, I am more than happy to be answering them with a drawing pad as well. So please do send those to me, and we'll start in a few minutes. Checking my email on the phone, so we'll see if any other questions came in. Nope. Okay, that's a good one. What is effect size? So we'll cover that. Very good. I'm going to cover them in the order that they came in. So I'm going to do the email ones first, and then go into effect size. Oh, good. So many coming through. Okay, z-test and t-test. Good. Why does saying the alpha level at 0.01 rather than 0.05 decrease the likelihood of rejecting the null? Okay, we can do that too. Very good. Let's just officially wait till 7. So that way people who are getting out of class or driving home, they can be a part too. Okay, so it is 7. So let's start. So let's get a new one here. Okay, so the first thing I'm going to cover is a question that I'm sure will help. So it's, can you please go over how to know which equation to use? So I'm assuming she's talking about the test that we did. So like z-test, one sample t-test. Independent sample t-test, and chi-square. So these are kind of the 4 statistical tests that we covered so far, right? So we also did skew and kurtosis and central tendency and stuff, but then we kind of started going into these 4 tests that are testing the difference between 2 groups, right? So depending on what 2 groups you're looking at, that will affect which test you're using. So here, for z-test, we have you have a population and one sample. Here you have also a population and one sample. Here you just have 2 samples and no population. And here the chi-square is kind of different in that you have like categorical like data. I'll also call them like count observations. So it's a little bit different. So, okay. I apologize for like looking like I'm staring at the camera because I'm trying to write legibly. Okay, so the amount of information you have will dictate which test you want to use. So for the z-test, you need, so what do you need? Whoop, oh my god, what happened? So you need, getting to the end of the tablet, this is tough. You need mu, which is the population mean, and you need sigma, which is the population standard deviation. You need these things to do a z-test. You also need m, which is the sample mean. So you need all these things. You can't do a z-test if you don't have the population mean, the sigma, the standard deviation of the population, or the sample mean. Now this is mu, this Greek letter. Sigma is standard deviation, and this is an m, not a mu, which is the sample mean. Okay, so that's the info you need. For a one sample t-test, you need mu, which is the population mean. And then you don't need sigma. So like the reason, if you have mu and sigma, you want to use a z-test. That's just the better way to go, because that means you're able to properly use the standard error of the mean. You don't have to estimate it. It's a more clean, more precise test. But oftentimes you don't have sigma, so you have to get by some other way. So here you need mu, which is the population mean, and then you need m. God, I'm sorry if this looks atrocious, but just listen. M is the sample mean. And then you also need SD, which is the sample standard deviation. So here is the same information, two means and a measure of variance. Here's the same thing. You have two means, mu and m, and since you don't have sigma, you have to use the sample standard deviation. So in this case, you'll wind up using the estimated standard error of the mean, which is the standard deviation of the sample divided by the square root of n minus 1. So here, it's just sigma divided by the square root of n, but since you don't have sigma, you have to make do with what you have, and use the standard deviation of the sample, which is gives you the estimated SEM, which is SD over square root of n minus 1. So okay, we can get by, we can compare our sample to a population, even if we don't have sigma. So we can get by with the standard deviation. So now with the independent samples t-test, you have no population. So what you need is two means, two sample standard deviations. And that's it. So remember that t equals m1 minus m2 divided by the standard error of difference. The standard error of difference is calculated by taking the square root of the sum of the squares of the standard error of the mean for group 1 and the standard error of the mean of group 2. And those are both calculated using the standard deviation of each group. Oh, and the sample size. You need sample size for these two. But you'll be given sample size. So here, you don't have any population parameters. So you have to make do with their two sample means, which you have up here. For chi-square, when you're going to use a chi-square, what you need is categorical data. Not just categorical, you need nominal data. So this is things like 1, 2, 3, 4, blah, blah, blah. No decimals or anything. You're counting like a whole person. So if you're in a recitation today, we did things like how many economists believe interest rates will go up or down. So that's like number of people. You can't have like half of an economist. It's either one economist or two economists or three, right? So it's like finite amount of data or a finite amount of observations. There's no decimal. So Ashley, for one sample t-test, there actually is a population mean. You need mu because that's the one sample. You have one sample and you're comparing it to a population. What you don't have is the population standard deviation, sigma. So for the chi-square, you need to have this type of nominal data. So number of observations, number of count. Like if you want to count, if there's a different number of fast food advertisements in rich, middle class, and poor neighborhoods, you would put the count of each number of observations like in each cell. So like you would have something like this. right? So let's say this is rich, this is middle class, and this is poor, and this is the number of advertisements, and you could have like 10, 20, 50, right? So you don't have like 50.5 advertisements in a neighborhood. It's either 50 or 51. So that type of count data is when you use chi-square. So chi-square is pretty easy to point out because it's so much different than everything else that we did. It's not distributional. It's not measuring, means or sampling distributions or anything like that. It's kind of a completely different data structure. So take a second to write that down, or take a screenshot or whatever, because I'm going to move on in a moment. So I think a lot of people were asking about this, both in email and in recitation and after recitation today. So just take a moment to get that. Sample size is always in here too. Like you need sample size because if you don't have sample size, then you can't calculate you can't calculate the standard error of the mean or the estimated standard error of the mean or anything. So sample size you'll have. And it came up in class maybe last week or the week before. What happens if you have samples of different sizes? That's not something that we'll cover in this class. In this class, we'll assume the samples are the same size. It'll say group 1, the n is 20, and group 2, the n is 20. So you don't have to worry about that just at the moment. Okay, so I take it that you have this now. If not, you can come back and review it when the video is available later, so don't fret. I am going to send out an email that says that you can go watch the video, so it'll be there for you in the near future. Sometime tonight, definitely by tomorrow. Okay, so that's how to use the tests. That's which tests to use. What else do we have? Effect size. So this is Julisa's question. So effect size. Effect size is one of those weird things. So, so far we've done effect size for T, which is Cohen's d, which I have to just double check. I think it's T over square root of n. I'll confirm this in a sec. And then for chi-square, we have C, which equals the square root of chi-square divided by big N, so the grand total, plus chi-square. Let me just confirm that that's true. Chapter 8 or Chapter 10. See, even after many years of doing this, you still have to double check once in a while. Power. Effect size. Oh no, Cohen's d is more confusing than this. So Cohen's d, so here you have, whoa, that's not good. How do I change it back to what I want? So it's t times the square root of n1 plus n2 divided by n1 times n2. So this whole thing is the square root. So for example, if your t, let's say t equals 4, then it's 4 times the square root of your sample sizes times your sample sizes. Okay, so that's how you calculate effect size. But the question was, what is effect size? So remember that you only do effect size when you reject the null hypothesis, right? So in rejecting the null hypothesis, you're saying we're fairly sure that we're going to make this decision that the null hypothesis, which states that there's no effect or that there's no difference, is not correct. So what you're saying in effect is that there is an effect. Let's say I'm measuring height in my class, and I want to know if gender has an effect on height. So I measure the men and the women in the class, and I do a 2-sample t-test, and I say my t-value is 4, my critical value of t is like 2.3. I reject the null hypothesis, so I'm saying there is an effect. My independent variable, gender in this case, has some effect on my dependent variable, height. So okay, there's an effect. Well, how big is that effect? Is it that, you know, so for gender it's tough because gender is binary. At least we consider it binary mathematically these days. But the idea is that how strong is the independent variable on the dependent variable? So for instance, what's a good example? Like, is there an effect on being shot? Like, does being shot have an effect on dying, let's say? That's a very strong effect because with relatively few bullets, death is almost certain, right? Whereas if you think about psychology and some of the things you've read in pop psychological literature, there's things like subliminal messaging, and subliminal messaging may affect how many things you buy. Like there was an example in maybe the second recitation or the third where we talked about subliminal messages, or maybe in the first recitation, subliminal messages and the effect of buying more concessions at a movie theater. And that question was asking what is the independent variable, what's the dependent variable. The independent variable is the subliminal messaging, and the dependent variable was the amount of concessions bought. And so, yeah, you might find a significant effect, like an effect may exist, but if it only moves the needle a little bit, if concession prices or concession purchases only go up a little bit, then you would say that's a small effect, right? So to get the idea of how big or relevant the given effect is why you need the effect size. And effect sizes may vary on the scale that they exist on. So like Cohen's d may not be directly comparable to a c that you would calculate with chi-square, but they're both getting at the idea of how strong is the effect of your independent variable on your dependent variable. So in this case, the subliminal messaging, like if I was watching a movie, I would normally buy $10 worth of concessions. But then if I watch a movie with subliminal messaging, I'll go and buy $50 of concessions, like quintuple the amount that I would normally spend? Or is it that if I watch a movie with concessions, I go from $10 to $12? So that difference may be significant if you have very small variance, which is possible, right? If your standard deviation is very small and it goes up $2, that would be a much smaller effect than if the purchasing goes up to $50. I hope that clarifies it a little bit. So effect size is basically saying how strong is the relationship or the effect that my independent variable has on my dependent variable. Effect size is weird because it's also contingent on the field, right? So like effect sizes in psychology are usually not very large. Maybe like 0.3, like a Cohen's d of 0.3. That's not a huge effect size. And things with small effect sizes can also be very important. So like, you know, if there's a drug that has a small but measurable effect on reducing cancer, then that's an important thing, you know? You don't have to have some gigantic effect size for it to be relevant. It just is a subjective kind of measure of your independent variable on your dependent variable. So that's effect size. Always, always, always calculate effect size if you reject the null. Even if the question doesn't ask, just do it out of habit. So Johnny, that's kind of subjective to the field. Typically, psychology, like, I mean, it really matters. It's kind of up to the scientist. Like, there's no hard and fast rule. So typically in psychology, a weak effect is an effect size smaller than 0.2, like a Cohen's d is smaller than 0.2. Medium effect is like 0.2 to 0.6 or 7. And a strong effect is like above 0.7. But it like really, it's really subjective. So like I wouldn't use that because different scientists and different fields may have different thresholds of what they find is weak versus strong, and it's a big quagmire. So I would just report the effect size. No, you don't need to understand what's a small or large effect, I would say, but you need to understand what the effect size is and how to calculate it, is what I would say. Okay, so we did effect size. Can we go over the difference between z-test and t-test and what information you need for each one? Okay, so we did what you need for each one. So I'll briefly go over the differences kind of more in depth. No problem, Johnny. And I'll get to your earlier question as well. I'm just kind of going in order. Okay, so z-test, t-test. So, like I said before, it's both population versus sample. So this is one sample. So for both z-test and t-test, a one-sample t-test, you're comparing a sample to a population. So if I want to know if my recitation of students is, if their height is representative of the height of all Rutgers students. So it may be that I have an abnormally tall or short class. That might be possible. So we can test that. So for doing a z-test, what you need is mu and sigma, because z, if you remember, is m minus mu divided by the true standard error of the mean. And the standard error of the mean is sigma divided by square root of n. So here's where you need mu here and you need sigma there. So you need mu and sigma. For a one-sample t-test, you just need mu. I mean, you need mu and sigma. You also need m and you need n, right? So you need these sample parameters too. Here you just need mu, you need m, you need n, and you need the sample standard deviation. So for here, for a one-sample t-test, you're saying, I don't have sigma. Too bad. I wish I had sigma, but I don't. So what can I use instead of sigma to try and figure out if I have some abnormally tall or abnormally short class? So you wind up using the standard deviation of your sample because that's what you have on hand. If you had sigma, you would use it, but you don't. So remember here that on your one sample t-test, it's m minus mu divided by the estimated standard error of the mean. And the estimated standard error of the mean is the standard deviation of your sample divided by the square root of n minus 1. So it's the square root of n minus 1 because when you use the standard deviation, it constantly underestimates the estimated standard error of the mean. Or it constantly underestimates the standard error of the mean. So if you were just to compare them, SEM versus estimated SEM, and you just had square root of n as the denominator for both of them, the estimated standard error of the mean would always be smaller, which is bad, right? You want it to be the same. You want your estimator to be almost identical, if not identical, to the actual number that you want, the standard error of the mean. So you have to do this square root of n minus 1 to correct for that. So you make the denominator smaller, which winds up making the estimated SEM a little bit bigger. It's just an important rule. It tends to be that the standard deviation in a sample is a little bit smaller than the population. So this is the difference between the z-test and the one-sample t-test. Although you use them both to compare a sample to a population, the reason why you would use a one-sample t-test is because you don't have sigma. Sigma is like the really important part that I'll even circle it with a red circle. So sigma is like #1 cool kid in the class. If you don't have sigma, you can't do a z-test. You can still do a t-test because you'll just use the standard deviation of the sample. So that's the difference. Gabrielle, I hope that makes sense. Now, if it's a two-sample t-test, if it's an independent samples t-test, well, that's totally different because now you have two samples and no population. You don't have mu, you don't have sigma, you don't use the standard error of the mean, you use the standard error of the difference. There's a lot of differences there between a z-test and an independent samples t-test. So I imagine this is what you were thinking about. Since they actually are testing the same thing, it just depends on which information. So Ashley, that was for the two-sample t-test. And I'm actually just going to confirm for the one-sample t-test. Oh, right. Okay. So I wasn't going crazy. So let's just go back for 1 second, and this will clarify things. So going back for one moment, so we have one sample t. See, so I knew this equation from somewhere. It was for one sample. Okay. Independent sample t. D equals t times the square root of n1 plus n2 divided by n1 times n2. So this is in chapter 8. This is in chapter 10. And then for chi-square, Gabrielle, if you find a question that you want to do, we can do it. So like, you know the test that will be on the exam. So if you look in the book for a question that you want to do, then we can do that. But you have to find the question for us to do. That's my deal. So these are the effect sizes. And then what chapter was this? 11, I think? No. So this was the chi-square chapter. Those chapters, Aprilyn, are in the old book, in the hardcover book. But I mean, you can just go by the topic. So the one sample t-test was its own chapter. The independent samples t-test was its own chapter. Chi-square was its own chapter. So just go by that. Go by the topic. So these are the effect size calculations. So for one sample t, it's your t statistic that you calculate divided by the square root of n. For the independent samples t, the effect size Cohen's d is t times the square root of your sample size 1 plus sample size 2 divided by n1 times n2. And then for chi-square, the effect size is c, and it's the square root of chi-square divided by n plus chi-square. And remember, the chi-square is just the statistic that you calculate. You don't have to square anything. It's just the number that you already have. So that's just to clarify for you, Ashley. And for me too, because I could have sworn, I was like, t over square root of n is something. So there you go. Okay, so going back to the list of questions, Gabrielle's looking for a question to do. That's good. Sarah, why does setting the alpha level at 0.01 rather than 0.05 decrease the likelihood of rejecting the null? Okay, this is a good question. This is a good conceptual question specifically because it requires you to understand what alpha is doing. Okay, so remember, I don't have to write anything right now. So remember that the alpha is your threshold for how much error you're willing to make. So when you say, I reject the null hypothesis, that decision that you make is either correct or incorrect, right? There either is an effect, and you are correctly identifying that there is an effect, or there is not an effect, and you are erroneously saying there is an effect. So there is a comfort of error rate that we tend to be okay with, and that tends to be 5%, which is what that alpha level is, 0.05. So that says for every 20 tests that I make a decision on, that I say that the null hypothesis is incorrect, there's a 1 chance in 20 that I'm going to make the wrong decision. And then I'm going to say I reject the null hypothesis when actually the null hypothesis is true. And I'm saying this very specifically in the words that I'm choosing because it doesn't mean that there's a 5% chance that the null hypothesis is true. It doesn't mean that you're 95% certain that there is an effect. Those are some common misconceptions that are made at this level of statistics, and those are incorrect ways of thinking about alpha. So alpha is basically saying how much error you're comfortable with in your decision-making process when you either accept or reject the null. On any given test, it may be true or false, but it's more about the long run. When you do many, many, many tests, how many of those decisions that you make will be incorrect. So okay, so that's alpha. And typically it's at 0.05, which means that, let's just say, let's say z. Let's say we calculate a z of 2.30 from some test, right? So this is m minus mu divided by SEM. Right, so we get this number. Now, let's say our alpha is 0.05. So we're comfortable with 1 test in every 20 being incorrect. Well, the crit value of z at alpha of 0.05 equals 1.96, right? So our value is 2.30. The critical value is 1.96. Our calculated value is more extreme than the critical value, so we would reject the null, right? That would be the decision you would make. You would say, okay, this decision might be the 1 in 20 that's incorrect, but it's more likely the 19 and 20, that is correct, so that's fine. But let's say our alpha level is 0.01, which means that actually I only want my decisions to be wrong once every 100 tests, not once every 20. So it's a much more stringent criterion in that I can't afford to be wrong 5 times every 100. I can only afford to be wrong once every 100. Let's say you're a surgeon and you don't want to kill someone every 20 surgeries. You only want to kill someone every 100 surgeries. Or maybe you want to kill someone every 1,000 surgeries. Let's say that the risk of an error is very great. There's a problem with making an error. So you want to make it very more stringent. So in this case, the error rate is more stringent. And if you go and look at the critical value table, you can find that the critical value of z, an alpha of 0.01, equals 2.58. So now, if you look at our z value that we calculated, 2.3, it is no longer more extreme than our critical value. Our critical value is actually more extreme than z, which means here we fail to reject. The null hypothesis. So here, what you're saying is, I don't have enough evidence, or, my mean is not far enough away from mu, given the amount of variance we have, as measured by sigma and the sample size, to say that this is something that to say that I'm rejecting the null hypothesis. And the reason why that is the following. Cool. So let's say here's your normal distribution. So here is a z. Yes, that's a good way to think about it, Johnny. So let's say z, here's negative 1.96, and here's positive 1.96. And remember that z is just measuring distance in standard deviations, or in like units of sigma, right? So this is almost 2 standard deviations away. This is almost 2 standard deviations away. Inside here, between negative 1.96 and positive 1.96, in this big bulge of area, is where most of your observations are. 95% of all observations are within 1.96 and negative 1.96 standard deviations of a normal curve, which means that there are 2.5% on either side still. So you have 2.5% of observations out here and 2.5% of observations out here. This is 2.5. So that's your 100%, right? So when you have a value of, let's say, let's go crazy with colors. Let's say you calculate something that's 2.3, right? This is our z that we calculated. So it's out here. So now you're saying, wow, it's pretty unlikely that the 2.3 value that I calculated is one of the majority of cases, right? It's kind of far out there in the tail. It's not one of these. It's something that's fairly uncommon, very fairly uncommon. So with an alpha level of 0.05, where my cutoff is at 1.96, then I'd say, yeah, that's extreme enough for me to say the null is not correct. But if we say, you know what, I actually want to include 99 observations, 99% of observations, excuse me. So I'm going to reset my critical value to 2.58. So an alpha level of 0.01 means that now, outside of here, there's only 0.5% of observations on that side and 0.5% of observations on that side. And inside here, right, so now all of this in the middle, and then all of this out to that critical value is 99% of observations. So nearly all of them. Only 1% of observations fall outside of that critical value. 1/2 on the positive side and 1/2 on the negative side. And so now your calculated z value of 2.3, this value, is now within that 99% of observed values. So you would say, well, you know what? If I want my calculated value to just be the most extreme 1%, well, it doesn't fall in the most extreme 1%. It falls in the 99 other percent. So I would then fail to reject the null. So that's why decreasing your alpha level makes it harder to reject the null, because now that value that you calculate has to be even more extreme when you make alpha small. And you could keep making alpha small, really, really small. It's important in areas that you expect to have lots of false positives. So like if you have an error every 20 observations and you're making, 1,000,000 observations, that's like 500,000 errors or something. I don't know. It's some high number of errors. So like if you're doing genome scanning, if you're scanning the genome and there are like tens of thousands of genes that you're observing, a 1 in 20 error rate is pretty big, So if there's 20,000 genes and you want to know what gene is associated with cancer or autism or whatever, just from measuring 20,000 of them, you'll have 1,000 genes come up as positive that are incorrect. Like it's just a 1 in 20, right? If your alpha is 0.05 and 5% of your decisions are going to be false, or going to be incorrect, then on large scales of numbers, you're going to also have large numbers of errors. So that's why sometimes making the alpha very, very small and being very stringent is important. Weird example, but counting a 90 as a B rather than an A. Therefore, tougher to get an A because you've raised the bar. Yeah, that could be a thing. Yeah, let's say you were using this class as like some threshold for some other class. Then if you changed and you only let people in who had an A. So if you change the threshold for A, you're going to select out the number of people that you're going to accept in. That's an interesting way of looking at it. Margin of error almost must be smaller. Yeah, that's the thing. So if your critical value is much higher, then you're getting fewer errors. But you're also increasing the number of times where you're going to say there is no effect when there actually is an effect. So that's something called type 2 error. So alpha has to do with type 1 error, which has to do with saying there is an effect when there's actually no effect, so a false positive. But when you're very, very stringent on alpha, you're also increasing the probability that you're going to say there is no effect when there actually is an effect, which is a false negative error. So let's say, for example, a false positive error is telling a person they have cancer when they don't have cancer. So that's a false positive, right? And you typically don't want to tell people they have cancer if they don't have cancer. That's usually a bad thing to do. A false negative would be telling a person they don't have cancer when they do. So that's also bad, right? You don't want to tell a sick person that they're healthy when they're actually sick. So there's a trade-off between false positives and false negatives in that the more stringent you are on false positives, you may be missing some things that are real effects. I hope that makes sense. Okay. So, Sarah, that's why when you decrease the alpha level, you decrease the likelihood of rejecting the null. Okay, Johnny, your first question. Explain the different types of confidence intervals. I got lost because they are different depending on the test. Okay, confidence intervals. Okay, so confidence intervals. They all follow the same general format, the same general look and feel, but the numbers you use will be slightly different. So basically, your confidence interval is your mean plus or minus some critical value times some variance, some sampling variance. So like so this can either be like SEM or estimated SEM, or if you want to go real crazy, you could do the standard error of difference if you really wanted to. So that's why I call it some sampling standard deviation. So some measure of the variance for a sampling distribution. So, okay. So here, this is your mean, right? The critical value, it could be T or Z. So if it's Z, it's either 1.96. Well, that's what the critical, I think what you're referring to is the critical value, maybe? That's this. So if you're doing a t-test and you're using a t-distribution, then it's the critical value for t at whatever degrees of freedom you have. So that's going to be variable on your sample size. If it's z, it's going to be 1.96 or 2.58, most likely. So for instance, if you had, let's say, a mean plus or minus 1.96 times, let's say your SEM is, I don't know, 2.3. So you could just multiply these two together. Let's just do that. 1.96 times 2.3 is 3.89. So it's your mean plus or minus 3.89. So if your mean was 10, then your interval would be 10 minus 3.89, which is 6.11, and 10 plus 3.89, which is 13.89. So this is your interval. This is your confidence interval around your mean. So this is a 95% confidence interval because the critical value you're using is for an alpha of 0.05. If you're using a critical value for an alpha of 0.01, then it would be a 99% confidence interval. And then this is the level of variance that you have. So if it's for Z, you would use SEM. If it's for T, you would usually use the estimated SEM. Or if it's some crazy question where you're wondering about the 95% confidence interval around some difference, you would use the estimated standard error of difference. This is not out of your wheelhouse. Like this is something that they could ask for. So it's not crazy. So that's confidence intervals. Was there more that you were interested in on confidence intervals? It follows that formula of your mean plus or minus some critical value. Okay, here's more. So how do you know whether you're using sampling SD or SEM or any of the others? I would know based off of what they give me in the problem. Yeah, so if you're doing a Z test, you're using the So like sampling SD is just one of these three. So like this isn't a thing. This I'm just trying to refer to either this or this or this. You're going to use one of these. If you're using a z-test, so you have mu and sigma, remember you have mu and sigma, then you use the SEM. If you just have mu and a sample SD, like you're doing a one sample t-test or a 2 sample t-test, you use this or this. So a 1 sample t-test, you'd use this. A 2 sample t-test, you'd use that. So it goes with what test you're using, is how you'd know. Like you shouldn't be calculating the estimated standard error of the mean if you have sigma. You shouldn't be calculating the standard error of the mean if you don't have sigma. So those are kind of mutually exclusive. And if you don't have mu, then you're not calculating this either, because you're going to have two groups, which means you have two estimated standard error of the mean. And then which one do you use then? You have to use the combination of the two, which is the standard error of the difference. Okay. Let me just check real quick if more emails have come in. Oh, 2 came in. Let's see. None regarding this class, unfortunately. Okay. Do you always have to calculate it? Well, the question might give it to you. 95% confidence interval, only if the question asks for it. So effect size, you always have to calculate if you reject the null. But confidence interval, only if they ask. Like, don't just go and calculate it. Wait till the question asks. I would imagine a question will ask on the first test because it's a new thing you learned. But you don't have to calculate it for every question. Only if there's a question that asks. Effect size, always calculate effect size if you reject the null hypothesis. If you fail to reject the null hypothesis, then stop there. Like, say I failed to reject and my one sentence. Okay, so let me go to JWell, and then I'll go to Ash's question. So I know it's going way, way back, but can you please review when we would add or subtract to get above or below the mean, if that makes sense? Add or subtract to get above or below the mean. Oh, I see. Okay. So you're asking about area under the curve. I understand. So let's do this, and then Ashley, I'll talk about your question after this. So we have a normal distribution. So this goes back to, I believe, the second recitation. Not always, Johnny. It depends. So let's say, so here's your mean, mu, and we have sigma. So we'll say we have sigma, 2 sigma, 3 sigma. And then here we have negative sigma, negative 2 sigma, oh, and then negative 3 sigma. So see how I always draw it with 3? Because that's the normal curve, right? You have 6 standard deviations, and go and review kurtosis if that doesn't make sense. But you should always have 6 standard deviations in one normal curve. Okay, so basically it depends on what the question's asking you, right? So the Z table in the back of the book always gives you the area under the curve from the mean to some distance in Z's, right? So if this was Z, this would just be 3, 2, 1, 0, -1, -2, -3. So let's say you want to know how many people get, greater than the average SAT score. So like SATs, for example, are standardized, right? And what that means is that the mean is always 500, like per test. Or this is how it used to be when I took it a million years ago. And then the standard deviation was 15. Maybe 600? It's 545. Wow. Don't mind me. 545. If this is not how the numbers are now, just use these for an example. That's fine. For 45, 55, 60, 60, 75, 80, 80, 95, 500. Okay, right? So basically all I did was I just added the standard deviations up and then down, right? Okay, so the normal curve is a really special thing because we know how many observations exist along the whole curve, right? So like I mentioned in a previous review, that from like 1.96 to negative 1.96, so like here, just below 2 on either side, like just below, we know that 95% of your observations are within those amounts, right? So almost 2 negative standard deviations and up to almost 2 positive standard deviations is 95% of your observations. And I'm kind of going over this in more detail in your question asked because it's kind of fundamental to how you know to add or subtract. So we know that a certain number of observations exist between any points, right? So here, so Johnny gave a question. I'll do it in one sec. So basically, the table in the back of the book gives you this number, right? So if you want to know how many observations exist between the mean and 1 standard deviation, you just go in the back of the book and you look up a z-value of 1. And that will give you some number, which is like 34 point something. And that's the percentage of scores that exist in this part of the curve. Now, green on green looks awful, but whatever. So if you just look in the back of the book for a z-value of 1, which says what is the area under the curve when my distance is from 0 to 1, so this distance here on the x-axis, the amount is 34% of all observations. Okay, if it's 2, it's some greater number. So that's what the table is telling you. It's telling you the amount from the mean to the standard deviation. So if you look up 3, it's going to give you the amount that's here. Right? So the biggest value it can ever give you is 50. But it doesn't include what's out there. Okay. So given that, let's do Johnny's question. So let's first use color, not white. Okay. So we have a mean of 103 and a standard deviation of 17. So out here is 120, and out here is 137, and down here is, let's not do head math because then you look like an idiot. So let's use the calculator. 103 minus 17, 86, and then 86 minus 17, 69. Right, so this is like a negative 2z, this is negative 1z, this is 0z, this is 1z, this is 2z. Okay, and so the question's asking, find the percentage below 115. Okay, so 115 is like almost 120, right? So first, and I always recommend that you draw a distribution when doing a question like this, because now you know, just right off the bat, you know that your z value of interest is going to be less than 1. It's somewhere positive and less than 1. So first you have to do is convert 115 into a z value. So you do 115 minus 103 and divide it by 17, standard deviation. And that is, what is it? 115 minus 103, which is 12 divided by 17, 0.71 if we round it. Okay, so that makes sense. Yeah, so Johnny got the same thing, 0.71. So that makes sense. It's less than 1, as we would expect. It's always good to look for this, because if you got something bigger than 1, you'd be like, okay, that doesn't make logical sense. I must have made an error. So now you look up 0.71 in the back of the book, which I will pull out right here. And table A, percent under the normal curve between the mean and z. You look up 0.7 on the left and 0.01, and you get 26.11. So what that's telling you is this area from the mean to that z is, oh God, I want black, please. Please, black, 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 dark red, okay. 26.11. So that's that area from the mean to z. But the question was, find the percentage below 115. So that includes all of this, right? What you know is 50%. So since you know it's 50%, because it's half of the curve and the curve is symmetric, right? So all scores below the mean cumulatively is 50%. So then you would just take 50 and add 26.11 and you get 76.11. So that's for this question. But let's say, just for funsies, let's say the question really asked you for this amount. So what percentage of scores fall between 115, 115, and let's say this is 123. Okay, so now it's something totally different. So now what you have to do is find this number. So from the mean to 123, let's just quickly do that. 123 minus 103 divided by 17 is going to be what? 20 divided by 17. 123 minus 103 divided by 17. So that's 1.18. So this is 1.18 is the z value. Here we know the z value is 0.71, right? So we already got this value, but now we want this value. So we look up 1.18 in the back of the book, which I'll do. Maybe if I can find it. Here. So 1.18 is 38.1. So we know that this whole value here, from the mean to that, is 38.1. But you don't want this big fat area here. You just want the thinner area over here. So in this case, you would take 38.1 and subtract 26.11, and you would wind up with, oh God, I'll just use the calculator. 38.1 minus 26.11 equals 11.99. So that means that this area between these two z values, this area here, oh God, not you, Siri. This value here is, what did I just calculate? 11.99. So see, that's where you would subtract, even though you're above the curve, right? You're above the mean. So it depends on what the question's asking you. You really have to read the question, draw the curve, and say, okay, what is the table giving me? The table is always giving me the amount from the mean to whatever z value I have. And what is it that I want? Do I want cumulative? Do I want partial? Do I want the most extreme values? It depends on what the question's asking. So here we had two positive z-values, things that were above the mean. One was add, one was subtract, based on what the question was asking. So I think the most important thing to do is draw a distribution, point out the values that they want to use, that they tell you, and go from there. Just logically say, okay, what pieces do I have? What pieces do I need? And then if you need extra pieces, you add. If you have too many pieces and you only want a subset, you subtract. Does that make sense? I hope that makes sense. So that's area under the curve. Okay, so now let's talk about Ashley's question. These are all great questions. I'm glad we have a very lively discussion. This is good. Okay, Ashley asks, could you explain what it means to reject or accept the null when it comes to chance? Like, what is it that we know that the answer is due to chance or not? Okay, so, okay, perfect. I'm glad I helped. But if it becomes unclear between now and the test, please do email me or come to office hours on Monday or whatever. So, it doesn't have to be the end of the conversation if between now and then it becomes unclear. So, okay. Chance. This is a tricky one. So, let's talk about chance. There is just normal variation, right? Like, not all men are the same height. Not all cats are the same level of niceness. Not all pizza places are as tasty as one another. There is just variation that exists. It's typically hot in Arizona, but there are also cool days in Arizona too, right? Like, there's variation. Not everything's the same, which is the spice of life, I guess is what they say, right? Variety is the spice of life. So sometimes when you observe a difference, it might just be due to the naturally occurring variation that exists, or it could be due to your independent variable. So let's do an example, just logic example, from something that means a lot to, so I'm from Long Island, so this means a lot to me in that, let's talk about bagel flavor. And let's talk about New Jersey versus Long Island. So not all bagels are the same tastiness, right? It could be that bagels from Long Island are tastier than bagels from New Jersey. That's a completely testable hypothesis. You could measure that in a variety of ways. So let's say that you score this on some test. I don't know. Let's say you ask 100 people to rate which one they prefer, or on a scale of 1 to 10, what's tasty. And so here they say that the New Jersey bagels have an average tastiness of 7, and here on Long Island they have an average tastiness of 8.5. Okay, now we know that bagels can range in tastiness from 0 to 10. Like, if you go to some real crappy bagel place on Long Island or in New Jersey, you might get a awful bagel. Like, that's really possible. It's not that every bagel tastes the same. So this difference of 1.5, right? There's a 1.5 difference here between 7 and 8.5. Is this difference just due to chance, which means like a product of normal variation? Like, could it be that I don't know, the 100 people I asked are real sticklers for the amount of water in a bagel or the chewiness, or maybe the bagel places that I chose just skewed, towards being less tasty. Like there's a reason, there's many reasons why. Is it just due to the normal variation that exists in the tastiness of bagels, or are Long Island bagels really much better? Now, I know where I fall on this spectrum. I think it's the latter, but we can test this statistically, right? When we test this based on, um, I'll get to that in a second, Tony. Based on how much variance you have, which you'll be, like in this case, would be using the standard error of the difference. But it could be any number of measures of variance that we've used, depending on what test you're using. Could be standard deviation, could be the regular SEM, could be the estimated SEM. All of these are in the equation one way or the other. So when we reject the null hypothesis, we're saying that this difference of 1.5 goes above and beyond what we'd expect due to natural variation. So yes, bagel tastiness can change. We know this. But this difference of 1.5 is more extreme than that. We're saying this difference is because Long Island bagels are actually better. We're saying that this is the actual winner, because normally we'd expect to see some level of variance, but not that much variance. Like, oh my God, 1.5, that's a big difference of means, right? So let's look at the equation. If it's mean 1 minus mean 2 divided by the standard error of difference, right? If this is very big compared to this, how much variance you have, then you're going to get a big t-value, right? And a big t-value makes it easier and easier and easier to reject the null hypothesis. So you're kind of taking that mean difference and putting it in the landscape of normal, everyday chance, normal variance. Because chance just means, oh, I close my eyes and I pull 100 people and their variance might be 1.3. If I pull another 100 people, their variance might be 0.8, So there's differences in how you do these samples and stuff. So that's what it means, right? If you fail to reject null, what you're saying is, yes, 7 and 8.5 are not the same number, but we wouldn't expect them to be the same number under a true hypothesis, under a true null hypothesis, right? We would expect there to be natural variation just due to chance, just due to just normal circumstances of each individual distribution, right? The tastiness of bagels goes from 0 to 10, so it's possible that we could have gotten 7. It's also possible we could have gotten 8 or 5. A difference of 1.5 isn't really that big, is what that's saying. So by referring to due to chance is just saying that in the broad view of the natural variation in these distributions, the mean difference that we observe is not very big, or not big enough for us to conclude otherwise. Would third confounding variable be synonymous with this? No, I wouldn't say that, though I see where you're coming with this. I see like how this question came up, like where it came from, but I wouldn't say it's synonymous, because chance is just natural variation, right? Like, is my cat really friendly because I just lucked out and got a friendly cat, or do I have some sense of choosing friendly cats when I adopt them? It's probably just due to chance. It's probably just that I lucked out and got a friendly cat, and that the normal distribution of things, there could be really friendly cats and not really friendly cats. Like, I just lucked out with a friendly cat. If you test it and I adopt cats over and over and over and over and over again, and I wind up always having a friendly cat, then you would say, this relationship that you're seeing between Nick adopting cats and always getting a friendly cat, that seems suspicious. That doesn't seem likely due to chance alone. Maybe there's something else going on. And that's the difference. That's when you would reject the null. Okay, so null automatically assumes there's no difference between these bagels, right? And that is probably due to chance. Well, yeah, a true null says that there's no difference. But instead of saying like no, so this is just, let's say, like no difference could mean like absolute no difference. So that 7 must equal 7. And if 7 does not equal 7.000001, then that's a difference, right? So like this is like a point estimate, it's called. So remember, like when you said what's the point estimate of the population mean? It's just a sample mean, just one number, right? So typically you want to have some range within which a null hypothesis can exist. So that's based off the variance. If there's a lot of variance, then, you know, like high variance, then you would expect that 7 and 9 might both fall under a null. Null, right? So like if you have high variance, you need a very large difference between two groups before you can say that there's a difference. There's a lot of noise, you know? But if you have low variance, then 7 to like 7.1, this might be significantly different. When you have very low variance, the mean difference doesn't have to be very big. If you have high variance, you need it to be big because you have to kind of really pull those means apart in order to find a difference. So any difference you do see, right? So like 7, while it doesn't technically equal 9, these numbers are different, right? 7 is not 9. So if you cannot reject the null, then you would say the difference here of 2 is due to chance. It's just due to the natural variation that exists. So like here, if 0.1 is significant, but 0.000001 is not significant, then if you wind up with this number, like even though it doesn't equal 7 exactly, it's still falling under the null because of how much variance there is. So like you could just close your eyes and put your hand in the distribution. You might pull something that's close to the mean, but not exactly the mean. And the number that you wind up with would be due to chance if it still fell under the null. It's a very tricky concept, but just think about it. I'm glad that makes more sense. Okay, so other questions. We still have like 13 minutes. Let me check the email again, see if more emails have come through under the wire. No. So take a moment to review your book, review the notes. And then, I'll be here till 8:30. So if something comes up, I'm ready to answer it. For the first exam, we're just answering these questions. It's going to be everything since we began. So skew, kurtosis, area under the curve, z-test, one sample t-test, independent samples t-test, chi-square, centrality, right? So mean, median, mode, things like that. And the second exam will be non-cumulative, so that'll be things that we cover after this. Then the final is cumulative. So you'll see these things again. When to use what? Yeah, so for the computational, you'll be given questions that you'll have to decipher when to use, like what test you'll have to use. So, if they say, if the question says something like, I have a national population of SAT, and the mean national score is 500. So automatically you would want to say like, oh, mu equals 500. And I have a sample of 50 students, well, okay, n equals 50, who took the SAT and their mean was 519, and their mean had a standard deviation of 8. And I want to know if this sample is representative of the national test scores. They say, oh, okay, well, I have mu, I don't have sigma, I don't know what sigma is. I have one sample with these characteristics, an n of 50, a mean of 519, and a standard deviation of 8. So I don't have sigma, so I can't use z, right? Z is a no-no. I only have one sample, and if I can't use z, then the answer must be a one-sample t-test. Like, that's the only thing you could use in this scenario. If you tried to calculate something else, you'd fall into some pit. Like if you tried using a z-test and you tried calculating the SEM, then you would say, oh, I don't have sigma, I'm stuck. So in this case, you would use one sample t-test. Or let's say they say, oh, I asked 100 economists and 100 students about their favorite genre of music. Either rap, what's that stuff called these days? Trap music? Sure, trap, and my favorite genre, ska/reggae. Not spelled right, but you get the idea. So I asked these people, and we found that 20 economists like rap, 70 economists like trap, and 10 economists like ska/reggae. Whereas here, it's probably even larger, 95, 4, and 1. This is about how it shakes out. So here it's like, oh, okay, I have counts of people. I have different numbers of groups. I'm going to use a chi-square. I can't use t-test, can't use z-test, can't use a independent samples t-test, so I must have to use a chi-square, which is what we did today in restation. They might say, I have a population whose mu is 10 and whose sigma is 2. I have a sample with a mean of 12. Is my mean different from my population? Like, is this... Oh, and n equals 200. How representative is my mean of the population? So you go, oh, I have mu, I have sigma, I have m, and I have n. So I can use z. Yay. Right? So z, it would just be 12 minus 10 divided by SEM. The SEM equals 2 divided by 200, square root of 200. So there you go. Now you can do, that's the z-test right there. So you'll have to read the question carefully, determine what information you have, and then there'll only be like one option based on what you have. So there shouldn't be a point where you're like, well, I could either use this or that. Then you don't have all the information that the question's giving you. There should only be one option. Okay, other questions. Moving on to the water bottle now. Yeah, so one sheet back and front. So there's no limit to the size of your text, like how small you write, but you can only bring one piece of paper back and front. You can bring your textbook. You can bring a calculator. Those are all for Thursday. For Tuesday, for the conceptual, you can't bring anything. It's closed book, closed notes. It's just a pencil, and that's it. We'll provide a Scantron, and we'll provide the test, and so you just bring a pencil. For Thursday, we'll provide scrap paper, so you don't need to bring that. And then you want to bring your formula sheet, which is a 1-page, 8.5 by 11-inch, regular piece of paper, front and back with whatever you want to put on it. So if you have 2 pages, then I would suggest you write smaller or organize better. So like I would organize a sheet by test. I would say, so like I bet on one side you could fit all of the tests, like z-test, 1-sample t-test, 2-sample t-test chi-square, and on the back you could fit all of the miscellaneous stuff. So things about confidence intervals, things about skew and kurtosis, things about centrality, things about area under the curve. I would be surprised if you couldn't fit all of that on one piece of paper. I'm sure it's possible, and I'm sure you could do it in a very organized and helpful way. The least helpful thing you can do is just bring a page from your notes. Like really spend time organizing it and using it in the most efficient way. Like the students who spend more time organizing their cheat sheet will have an easier time on the test. Let's just put it frankly. Okay, is the conceptual mostly definitions and what formulas to do if we were to do so? How do you suggest we study? So, no, it's not just definitions. It's going to be things like, there's some definitions for sure. So like, what is the standard error of the difference, right? This is an example I gave in recitation. The correct answer is not, oh, it's the square root of SEM1 squared plus SEM2 squared, because that's just a computation, right? It's just a formula. So you have to actually think about what all the different pieces do and what information they convey. So like the standard deviation of the standard error of the difference is the standard deviation of the sampling distribution of differences. All right, so that means something. That means that the standard error of difference is the average distance from any mean difference of samples to the grand mean in the sampling distribution of differences. Like it has a meaning. So knowing like kind of those deep conceptual meanings of things is important. But then I'll also ask you like a question that came up earlier, like why does it get more difficult to reject the null when you change your alpha level from 0.05 to 0.01? Or something like if you were to change the amount of people in your samples in a 2-sample t-test, does it increase or decrease the probability of rejecting the null hypothesis? So think about the relationships between all these different components and what your final decision is on a null hypothesis, right? If you have small variance, whether that be standard deviation or SEM or SED, that'll typically lead to making it easier to reject a null hypothesis, right? Because then, given a mean difference, that mean difference seems larger in the context of small variance. If you increase sample size, it's typical that you will make it easier to reject the null hypothesis. Don't just take my word for it. Actually look at the equations and see that that works. Change n. Like I would literally just sit there and say, okay, what's my equation? M1 minus M2 divided by SED. SED is the square root of SEM 1 squared plus SEM 2 squared, and both SEM, so let's just say SEM1 for example, is SD1 divided by square root of N1 minus 1. So these are the, and we'll just put, just to be complete, SEM2 equals standard deviation of group 2 divided by the sample size of square root of n2 minus 1. Right, so now we have all the components. So this is t. And let's say we have a critical value of t equals 2.07. So that's based on some sample size or whatever. So I would literally, this is what I would do. I would sit here and put in numbers, right? I would just say, okay, let's see if my standard deviation is 5 for group 1 and 7 for group 2, and my sample size for each is 10. So the sample size will always be the same for both groups. But then I would just calculate this out and say, okay, that gives me some value of the SED. What happens if I change these numbers? What happens if the standard deviation gets bigger? What happens if the sample gets smaller? What happens if the sample gets bigger? What happens if the mean difference gets bigger or smaller? Seeing how that affects your decision to accept or reject the null hypothesis, I think will help you approach getting comfortable with all these concepts. And I would do that for each equation to really say, okay, what is each individual component bringing to the table when I make a decision about the null hypothesis? I think that's a great way to get comfortable where the conceptual test is not so threatening. Also thinking about, distributions generally, thinking about, what the null hypothesis is. So like, what is the null hypothesis? It's that like the sample mean equals the population mean. Equals mu. So that's for like a z-test or a one sample t-test. Or like sometimes you'll see it as mu sample equals mu. Because mu sample is the mean of the sampling distribution. That's in the textbook. So mu sample equals mu is the null hypothesis, right? So if you then find that mu sample does not equal mu, then that's when you reject the null hypothesis. Things like that. So I would suggest just getting familiar with your textbook, getting familiar with these equations in depth. Like you should be like the formula sheets should be secondary. You should be at a level of comfort where you know all the equations. Like if you can do that, then you are probably in a good position for the test. The formula sheet should really only be there for reference and not as a supplement to what you've studied. It should really only be, oh, let me double check to make sure I'm right, and not, I don't know, I have to rely on my sheet. So if you're at the point where you can do that, then I would say you're approaching a comfort level that is appropriate. So definitely do not underestimate the conceptual test on Tuesday. And you have 6 days. So really just go at it, I know it's like not, it'd be way easier if I was like, oh, here's this other book that's really great, or oh, here's a YouTube channel that I think would be really helpful. I know that'd be much easier, but I think if you just get in there and think about the mechanics of all these equations and think about what it is you're trying to do, you're trying to parse out, the difference between two groups in an environment that has normal variation, kind of enveloping yourself in those ideas is really the best way to prepare for the conceptual. If you take the quiz will probably help you. Ava, no, so you can't bring a formula sheet to the conceptual exam. I mean, like for the computational, you should be at a point where it's all like secondary. But if you take the quiz, the online quiz, which is available, is it still available? If it's still available, take it, because that will give you some insight onto how Dr. Kilianski writes questions, and that's very useful as well. So take that if you haven't. If it's not available anymore, try to find someone who has that you can talk to, and that will be helpful in just getting a feel of how questions are worded and what you can expect. So I'm going to end it there. Yeah, so I just said that like if you're making your cheat sheet for the computational, it should be secondary and anyway, I'm just saying you should be really comfortable. Yes, so listen to what Johnny's saying. If you have a question, please do email me. Um, I will have office hours on Monday 1 to 3. I expect people to be coming often. Like, it's the day before the test, so I expect office hours to be pretty full. If a lot of people all come at once, we can go find a classroom or something. That's fine. If not, then we'll just be at my office, which is Tillet 429. And I think that's it. So this will be available to watch again if you want to review these things between now and Tuesday. I also have last semester's review on my website, which I'll just put up here, because then, students from last semester may have also asked questions that could be helpful to you that maybe we didn't cover today. So if I could just plug where that link is. So it's nickfox.net, NETLIFY.com. Yes, Tillet 429 is my office. So if you go there and you scroll down to teaching, you'll see links for these same type of reviews for when I taught this class last semester in the spring of 2017. So students who have previously taken this may have asked questions that will help you as well, maybe things you didn't think of, or maybe I explain things clearer then too. So they're worth watching. I have one for each midterm and for the final. So check that out. I'll send you out an email with the link for this video once it's done uploading, which will probably be later tonight or tomorrow. And then good luck studying. Yes, that's right, Johnny. Thank you. So good luck studying. Email me if you have questions. Come to office hours on Monday till at 4:29, and that's it. Thank you for coming by and making a very lively review. So I will see you on Monday if you come by. See you.